Good evening, everyone. Welcome to the fifth session of Mechanical Unit Operation course discussion. Today we are discussing about the size enlargement operation. Unfortunately, we don't have any live audience today, but at least we will hope that someone will join us in between. So now I am sharing my screen. So okay, so all of you can maybe you can able to see my screen. Now I am going for the presentation. Okay, so this is the today's topic, that size enlargement. We discuss about the size reduction and transportation and storage and transportation of solid. Now we will discuss about the why we need size enlargement and what are the methods in this, particularly for the assignment of this fifth lecture. Most of the things will be covered as a theoretical portion only. Some examples are there. So for that we will go through the in detail description of the major topics in this size enlargement unit, and at the same time we will also try to solve some simple examples which can be helpful for the solving in an assignment. Okay, so first thing is mechanical unit operation. Size enlargement is the week 5 course. There are 3 different lectures: size enlargement method, and there are 2 lectures on size enlargement equipments. Now as you can see, there are this is the outline of our today's discussion. We start with the different methods and what is the objectives, why how these different agglomeration methods works, which is the GOT mechanisms which are used. There are some examples on it. So I covered all the major topics which has some examples in the assignments. Then size enlargement equipment and spray processes. Okay, so first and foremost question is why size enlargement required. Okay, so we will start with that because we discuss about the reduction, and that is justified also, that reduction is required in order to reduce the size of the solid particles. Now why size enlargement required? So definitely when we talk about the fine particles, they are very difficult to handle because their density and other physical properties are such that they will be sustain some difficulty in order to handling them, and they cannot easily flow also. So finer the more finer the particles, the greater is their surface area, and the more surface area particles has very difficulty in handling. Why? Because they have greater because gravitational forces acting on the particle may not be great enough to keep them apart. So that's why they can generate dust, they can issue some flowability issue. Then particles, that kind of flowability of particular system can be improved by using glidants. Now what is a glidants? So if we talk about the glidants, then the glidants are the very fine powders which we are using, which are capable of reducing interparticle friction when we mix them with solid particles, and they reduce interparticle friction by forming the surface layer on the particles. So whatever particle we have like this, they are forming the surface layer above the particles. So these are the chemicals which are known as glidants. So there can be combating the effect of friction arising from the surface roughness. Now, but when we are using this glidants and all, then the optimization of particle size is the major issue. Or whenever we are talking about the size enlargement, then also particle size optimization is the far more important phenomena due to for improving the flow properties of solid. Okay, so these are some basic things which we need to keep in our mind. And if we talk about the more, then as fine particles may be difficult to discharge from hoppers, as we already discussed in the last storage and transportation unit, that if we have fine particle, then they can able to stuck in this kind of area, and they can cling to the walls, and they sometimes they are forming the bridges. So only this can be flow or this cannot be flow. So this section of the fine particles cannot be flow. They make some bridges at the point of the discharge. So this is also one major issue why we need enlargement, size enlargement. Now, although such problem can be minimized by vibration or by mechanical stirring. Here, if we provide the mechanical stirring or some vibration, if we provide some vibration motor and it provides some vibration, then also we can easily remove this kind of particle. But the satisfactory solution may be to increase the particle size. This is that can be the satisfactory solution, because then the transport and all other application of the solid particle can also we can perform easily. So that's why we can convert them into the aggregates. Now there is one another issue. If we use the fine particles, then they have some serious environmental and health problems. Definitely, as we have some silicosis and some due to some asbestos, there are many health issues are going on, including the carcinogenic issues. So because the small fine particles form dust clouds when loaded into the vehicles, that may become dispersed over the long distance in the windy condition. If windy conditions are there, then the small fine particles can go for the larger distance and they disperse into the climate. Even if fine particles are inert, serious respiratory problem can result because fine particles can easily inhaled by the human lungs. It may be noted that particular health hazard imposed by asbestos is largely associated with the size, range and shape of particles and their tendency to collect in the lungs. So we already discussed about the asbestos health issues. So these are also reasons why we go for the size enlargement. Now, size of particles may be increased. How can we increase the size of particles? They can be increased from molecular dimension by growing them, by crystallization from both solution and melts. We can do one thing. We can melt the solid particles and convert it into the liquid form, and the liquid can be again converted by using crystallization. We can convert them into again solid and large solid particle, or you can say enlarged solid particle. So that is also one way. And desired particle size may be also achieved by building up fine particles. There are two methods which we can use for achieving the desired particle size. One is the production of. Why we go for the each and every method? Because there are some questions in assignment which we can able to solve if and only if you have the very well understanding of the theoretical concept. The first method of getting the desired particle size is production of fertilizer granules by agglomeration or by repeated coating process. So sometimes we use the repeated coating as well as agglomeration process in order to go for the size enlargement in fertilizers majorly. The another process is formation of pellets. In pharmaceutical majorly they form the pellets or pills for medical purposes by compression of particulate mass. When we apply the compression of small particle, then we can able to form different kind of pellets and pills kind of composition and in the shape which we can use majorly in the medical sector. Often with the inclusion of the binding agent will impart necessary strength to the pellet. For pelletization process, we have to use the binding agent. Now, what is the actual definition of size enlargement? So, size enlargement is a process which is whereby small particles are agglomerated or otherwise brought together into larger, relatively permanent masses. So we need to convert the small particles in the terms of agglomeration, or we have to take them into the they are brought together into larger and relatively permanent masses in which original particles can still be distinguished. We can able to distinguish the original particle at the end also. So there are some process. If we use some material like glidants and all, then there will be very difficult to separate the original particle from the glidant material. So there is one important aspect that we can be able to get the original particle back by any distinguishing process or any separation process, or we have to use the only original particle rather than using Clydens and all. Now, what are the objectives of size enlargement? The major objective is in the agriculture, chemical granules or pharmaceutical tablets. These are the two areas where we use the active ingredients. So active ingredients needs to be taken care of in the farm. It's difficult to write on the screen, so please bear with this my handwriting. So it's important to use active ingredients and convert it into the tablet form or pellet form. Tablet or pellet form in order to use them into the farm as well as in the human being body. So that's why this is a very major area for the size enlargement. In that you have to provide a defined quantity to facilitate dispensing and metering. We need to what are the you can say outcome of using tablets and granules: improved flowability, creation of segregating brands of powder ingredients. If we talk about the another areas like briquetting of waste fines. So when waste treatment plants are there, they basically you convert into the briquette form, and this that can form if we have waste fines are there, then they will be very difficult to handling of that fines. So we can briquette them. In that you can eliminate the dust handling hazard or losses. Granulation of fertilizers. So fertilizers, as you have very well-known example. Urea is we generally all the in granular forms. So mainly in fertilizers we are using a granular form where we are applying it into the farm. Now increase bulk density for storage in tableting feeds. We can increase the bulk density, yeah, definitely, and we can control of solubility of instant food products. So we can control the solubility of instant food product in order to use size enlargement. Now agglomeration methods. So what are the different methods which is used for the agglomeration? That is very important then, because agglomeration is our main focus. How can we agglomerate the different types of dust or fine solid particles into a final enlarged material? So one is a granulation or agitative agglomeration. So in the agglomeration we are providing some granulation. So for granular formation, or we can say the agitative agglomeration. So in that we are providing some agitation, some turbulence to our fine particles. Then that we use by using that agitation, our particles are agglomerate with each other, and this can also refer as a granulation. Another is a sintering. So sintering is the major phenomena when we induce heat. So agglomeration by using the thermal means. So in sintering we provide the heat to agglomerate the particle, which either leads to controlled sintering of the particle bed or induces sintering or partial melting of binder component of it. So like you can see, for controlling the particle size in sintering, we need to use some binder component or some example some polymer material which can control the size of the particle. And if we go for more different methods, then there is a compaction and compressive agglomeration. This is a easily understandable process that if we provide a compaction and compressive process, then our particles or fine particles, when in the presence of binder, it can convert into the size enlarged particles, enlarged size particles. In this process, if you define it, then processes where the mixture of particulate matter is fed to the compression device, which promote the agglomeration due to pressure. We pressurize the solid fine particle to go for the agglomeration. Either continuous sheets or strands of solid material produce, or some solid forms such as a briquette or tablets. We can produce briquettes, tablets, or some continuous sheets in this kind of compressive agglomeration process. Now, what are the different stages in the agglomeration rate processes are there? So here, as you can see, there are agglomeration, this is the basic steps which I include over here. And we can start from the spraying. We can use the binder material which can bind our fine particles or solid particles, and that binder which can we can spray it on it, and then by spraying them, this binder material can form the different layer on our solid fine particles. Then moistening, that binder material come into the contact with our particles, and then we form the liquid bridge. By using that, we can moisturize our particles or fine particles, and then that moisture can eventually solidify, and that is known as a we can also known as a solid bridge. The solidified portion can at the end convert into the agglomerates. So we can get at the end agglomerates of the solid fine particles. This kind of agglomerates is also known as there are different types of name we can use for different kind of structure. If we just talk about this structure, then it is known as a blackberry structure. So this is a one simple method in which we spray our binder material, which can make the liquid bridge, and at the end we moisturize all our solid fine particles, which can eventually solidify and converted into the agglomerates in the end. Now if we go for more detail, then all this, if we start with the weighting of the conveyor particles, these weighting properties, we need to control the properties like size, bulk density, attrition, dispersion, flowability. Then this liquid particle is that can be take part in the growth portion. In the growth portion, two different kind of solid particle have some liquid bridge inside it, and then it can consolidate our whole particle, and at the end we will get a weight granulation, and we can again break them into our desired method. So if you talk about the different parameter which we need to focus, then for the granule property, it must be the function of size and void edge. Void in two different parts, there is a void portion or empty portion is there, so it is a function of that, and that all size and void edge can be converted, can be a function of the operating variable plus the material variables. What at the time of operation, what are the variables we are focusing, and at the end, if we talk about how we can define the operating variable and material variable, that go into the process design and formulation design. When we design it, we can convert, we can go for the after process design, we can operate the variable and material variable, which can able to use for the size and void edge of our particle, which is a function of size and edge, and then we'll get the final granular particles, which are based on some size, bulk density, attrition, dispersion, flowability properties, some of the physical properties. So these are the different stages. We don't need to go for much detail, but yeah, you need to understand that which are the steps required. And if you go for by the typical textbook language and some professor lectures also, this granular growth and granular breakage, you need to you understand. I think you understand. In that one, nucleation, small fine particles are converted into the bigger particle, and that the bigger particle by using coalescence. In coalescence, what happens? That particle is come up contact into the another bigger particle, and that both particle can be combined together in various morphology, and then layering of our particle can be done. And we either that may be coalescence, or either there will be coalescence, or there may be layering. In the layering, you can see the small fine particles. This big another particle can layer. The small particle can form the layer on this another particle. And if you talk about the breakage purpose, then this kind of bigger particle can settle into the small fine particle, and if one particle can be fragmented into two different kind of ununiform, uneven, different morphologies or different shapes, and sometimes wear can also occur. So because of wear, some particle size reduction is there, and you can get a free fine particle over there. So aberration transfer is there when two different kind of particles are there, and that come into contact, and there may be aberration process is going on in between two and you can get a different uneven morphology of different two particles, solid particles. Now if we just going for the weighting and nucleation or we can just go for the whole overall process of agglomeration, then here you can see that in weighting nucleation, liquid binder can be added into the powder mixture, fine powder mixture, and then weighting process is going on, and at the end nucleation of the particle is started. In the nucleation you can see small agglomeration is there. This nuclei can be growth into the bigger growth and with the help of coalescence, and at the end you can find that they can reach up to the stage which you can say that this is the consolidated stage of the fine particles, and this consolidated stage may be gone through the attrition and breakage in order to control the size, as well as in order to some operational we use in some operation, then there may be some attrition and breakage can be occur. Now if we talk about the granulation and that to agitative granulation, then here you can say that this is a process vessel. In process vessel you feed some fine particles with some particle distribution is there. So if you can say different various size of particles you feed into that, and in this agitation is provided, which is you can say is a function of different kind of motions, and at the end you will get some product which has some enlarged particle or size particle which is in some pellet size, or you can say in some consolidated particles which has a different kind of particle size distribution and which is a different from the original particle size distribution. Okay, so this is the agitative granulation where we put the material into the process vessel and we provide the agitations or mixing of that in the process vessel for the fine particles. And here you can say this is a binding agent which we are providing some liquid materials which can bind our total all the fine particles. This is all about the agitative granulation, which is discussed by Professor in detail. And there is another method which is known as a compressive granulation. In compressive granulation we are using the two different sections in which in between our all solid particles will be gone through the compression forces. Here the same different feed distribution is there. Fine particles are there. We are providing into the compression vessel. Compression vessel is also in the function of size, voidage, strength, different surface properties. Here we provide the pressure. So pressure, overall pressure is also depends on all the different pressure forces apply on the different particles. And at the end you can see we can make some pellet or pills like a pills kind of structures of solid particle. Here as you can see here again both the final product final particle size distribution is different from the initial particle size distribution. So this is the major two different granulation process. One is a agitative and another is a compressive. If you go into the another details of size enlargement, then if we go for the whole overall typical agglomeration circuit, then it is look like this. So maybe this thing will already was already covered into the lecture, but you just go through it again, and by my lectures you can get some idea to solve some example of some basic questions or basic questions based on the theoretical processes for in that assignments. So here you can see the typical agglomeration unit has this kind of beans where we start to feed our powders. Then it can go into some blending where we blend some binder. Here maybe we can blend some binding material or binding agent with our solid particle, and this reblend or ribbon blend or different kind of blender we are using, and from that it will go into the premix bin. And here we can use some moisture or water. If that also in every process is not required, but if it is required then we can use, otherwise it's not needed. Then we will go to then blending material can go into the blending can be unified all the particles, and then it can be sent to the premix bin. Here we are use the binding fluid, then it will go into the granulator or agglomerative unit. In the granulator unit, where it converts into the granules, and then we classify it in order to use at a final product. So whatever the oversized material is there, we will use to the granule bin, and then it can be converted into the final shape, final form of application. Or whatever undersized material there is there, we again do milling of that material, and we are again because it has agglomerated particles, so consolidated big particles are there, so it is required to mill while using it again or recycle it again with the fine material. So this is a typical agglomeration circuit which is there in textbook, so which you can follow. Now there are some questions in our assignment on the basis of growth mechanism. So there are basically two different growth mechanisms are there when we brought together different fine particles. So one is the perikinetic processes. Okay, so what is a perikinetic process? If we talk about the perikinetic process, then sorry, I am just waiting for so the perikinetic process are only attributable or only because of the Brownian moment of the particles. So when our material is in the static condition, which is not in moving, then also there is some Brownian motion is going on. So we can say that the perikinetic process is based on the Brownian moment. And the double layer repulsive forces and underwire attractive forces may both operate independently in dispersed system. Whenever I talk about the dispersed system and perikinetic process, then double layer repulsive forces as well as underwire forces both are attractive. Attractive forces can take place. And you have to always remember that perikinetic process is because of the Brownian moment. This is a typical formula where how we can represent the perikinetic process. dt cube is equal to a1 plus b1t. You will get the value of a1 and b1 when they have in different unit also. So you will get the value in any of the problem. You will get the value of a1, b1, and you need to find the dt. So if you talk about the orthokinetic process, then it occurs when the perikinetic process is supplemented by the action of eddy current. When we apply the eddy current or any turbulence to the perikinetic process, then or by in the means of stirring or flowing them, then this orthokinetic processes comes into the picture. And the typical formula for the orthokinetic process is the log of dt by do A is equal to E2 plus B2t. Here A1, B1 and here E2 and B2. There we can represent it in the form of x1 plus y1t, but x plus yt or A plus bt. But here that A1 and A2 is because of, you can consider that both are the different. If we talk about perikinetic and orthokinetic, because orthokinetic has some eddy current or some turbulence in the order to stirring or some mixing of the solid particles. So this is all the reason. That's why both have different constant values also, and it depends on the processes, and the constant value will be provided if there is any example on the basis of growth mechanism. So we will try to solve one example. In that, particle of initial size of 0.03 mm are granulated by an equipment where operation is governed by perikinetic process. So here we need to follow that. Here our process is perikinetic. What is the size of granules obtained after 75 seconds of operation of constant A1 and B1? As you can see that A1 has a value of 350 millimeter cube and B1 has a value of 12 millimeter cube per second. So these are the different values you already get in your example. or any numerical, if you anyone will be there, it will be there in exam or any assignment. So the initial particle size you need to keep in mind is 0.023 mm, which is a very fine particle, not much fine, but yeah, it's a comparatively fine particle. Now we have, for the perikinetic process, we have the equation dt cube is equal to a1 plus b1t. Now we talk about the value, then we have value of a1 which is a 350 millimeter cube, and value of b1 is a 12, and t is nothing but the time. So here our whole process is going up to 75 seconds. After 75 seconds, what is the dt cube? We will get 12.1250, and at the end you will get the value of dt, which is the final particle which you get at the end of the size enlargement process, which is only which is nothing but 10.77 millimeter. So you can see that from 0.23 millimeter to 10.77 millimeter, this is a huge difference. So that's why according to some application they require this size enlargement. Now okay, so this is that's why that kind of examples are there on the basis of perikinetic or orthokinetic process. You can easily solve by just putting your constant value which is available in the example. If you talk about the different method, sorry, okay, so different method for size enlargement, or you can say different size enlargement equipment on the basis of different applications. So some of the method and equipment I took from the professor's slide because they are important in order to solve your example, so your assignment examples. The first is tumbling granulators. So tumbling granulators are, you can say, tumbling process is going on for making the granulation process. In that there are two different methods. Drums can be used and this can be used, and you can say the granular density is moderate, the particle size is around 0.2 to 20 mm, capacity is 0.5 to 800 ton per hour, and whereas spherical granular you can get in this tumbling. So there may be an equation on basis of spherical granular from where you can get this tumbling granulator, and the application is in fertilizer and in other words. And then mixture granulators, where you provide the mixing process, that continuous high searing is there and batch high searing is there. The continuous batch process are different, low granular density and moderate granular density. Continuous can be handled cohesive material, both batch and continuous, as well as viscous binder, non-wettable powders. Both can be applied. They are using for different pharmaceutical and chemical industries. Now, fluidized granulators. So fluidized granulator, as the name suggests, we are using the fluidization method. So we are applying the fluid to fluidize the solid particle. The fluid beds, powder beds, oyster bed, Worcester, coaters. These kind of different fluidized granulator are used, which has a product size of 0.1 to 1 millimeter. Granular density is depends on if agglomerated it's low or layering is there, then moderate. There is a different capacity, and you can go for the fluidized granulators. Why? Because they are flexible, relatively easy to scale up, difficult for non-wettable powders. You need to go for some disadvantage also, and viscous binders. So viscous binder and non-wettable powder you can't use into the fluidized granulators. And same as the drying air handling requirements will be there. In continuous operation, we will be using in fertilizer, inorganic salts, food and detergent processing, some pharma processes, and at the end, the centrifugal process, say indurator. Centrifugal granular is, we can say, we provide a centrifugal motion which has a granular density up to moderate to high, capacity up to 200 kg. Is a batch-wise process that will be used for the powder layering as well as coating operation, and it will also again used in the pharmaceutical, agriculture, chemicals. So major, this is size enlargement operation. Majorly you can find into the agriculture, agrochemical and fertilizer industry, pharmaceutical industry is major, because at the end product you want to use your active ingredient in some form, as we already discussed. So you have to remember all these things. Into the palette, or you can say granules, or palette granules, or peel, different kind of form. Now we will go to the little detail of some kind of granulators, because it may be helpful for the same thing for solving some of your assignment problem. So tumbling granulators are basically two types: disc granulators as well as drum granulators. So if we talk about the disc granulators, then as you can see here that this is a whole picture of the disc granulators. Here you can see the recycle we start from the first. Okay, so this is the whole particle where this is a binding units or solution sprays are there, and this is a scraper. So scraper is control the size of the particles. There are some just give me 2 seconds. Okay, so your concentrated solution will be fed over here. It will be sprayed on your particles, and then fine particles can be mixed by tumbling process of the material of the equipment. And this is a disc kind of granulators is used. This scraper is used to control the size. Some undersized materials are there, they still remain there. Rotation is provided. Some of these fines are recycled back. Product will be given at the end. And this is how it actually looks like. So you can see that this is like this, turning the disc, some motor, speed reducer, connecting plates, motor transfer. All this kind of motor is provided, and there are some scraper supports. So scraper can be controlled. This is the same thing of solution spraying, and scraper can be used to control the size of the particles. Now, this disc granulator is generally used for the coating of feed material built upon the disc thickness, which is very easy. As you can see, you can just put your solid particle and some liquid, and then coating will be taking place. Surface of pen may also be lined with the expanded metal and abrasive coating to promote the proper lifting and cascading of particulate pen. So lifting and cascading of particulate pen, this kind of inner portion of the particle is also coating. Solids are typically fed by either volumetric or gravimetric feeders. Any kind of feeder you can use, and there is some critical speed on which you can just rotate these whole disc granulators, which is single particle is held stationary on the rim of the disc due to centrifugal process. So that is the same you can get when you equate the centrifugal force with gravitational force. So from that you will get the value of NC, or you can say critical speed, which is nothing like NC is goes under root of G sin phi and upon 2 pi square t. Phi is the angle of disc to horizontal plate, d is the diameter of the disc. So what is the typical operating ranges of the critical speed? That is, critical speed is always 50 to 75% of what is the operating range of equipment? So we can operate the equipment of 50 to 75% of NC critical speed, and at what angles? For angles generally 45 to 55 angle. If the speed is too low, sliding will occur, and speed is too high, particles will be thrown off the disc. You already visited this kind of concept in the roller and ball mills. Now we have one example here on basis of disc granulator. It's a disc granulator having a disc diameter of 17.5 meter and this angle 53.5, used for the size enlargement operation obviously. So what is the critical speed of this disc granulator? So now here we are using the typical critical speed formula which we just saw, under root G sin phi upon 2 pi square t. So this is the same formula. Here we apply G is a 9.81, sin phi we are 53.5 degrees there. So just look into this kind of problem, so you can get some solution for some of our example problem. So here you can see NC is directly proportional to under root G gravitational acceleration, it is inversely proportional to the diameter, under root diameter. So NC is proportional to d raised to minus 1 half. On here you can provide the value of different 17.5, it's a disc diameter. Okay, so maybe I just put some mistake here. It's a 17.5, so it is 8.5. But at the end you will get the right result only. So I calculated the correct NC is equal to 0.33322 rotation per second. But if you go for the RPM, then there is a 20 rotation per minute. This is some explanatory examples. Sorry. So this is explanatory examples in which you can find the critical speed, like we are using the simple equation, and you need to just provide the values into the equation. But don't consider this. You can put the actual D value and then you will get the answer. Now there is a different types of tumbling granulator, which is also tumbling granulator, but which is known as a drum granulators. Here we are using the drums rather than this disc. So in the drum granulators, solid can be fed by this chute and it can be go inside. Here you can see there is a liquid lines are there, so solid will be go from here, and this liquid line can be spray over the solid material. And there is here also scraper bar is there, which can control the size of the material. Then as you can see, this is the inlet tumbling and there is a outside tumbling, and at the end exit chute can give our final product. So this is a simple same kind of material, and it can get rotated by any of the direction. There is a one good thing that drum regulator can also be rotated in any of the direction on the basis of your application. And this is a original picture of the drum granulators, as you can see here. So this is a very easy to understand, as we already discussed about this granulator, and this is not just tumbling devices. Now if you go for the more detail, then this kind of granulation drum is there, which is a mechanical construction is showing over here. It is liner, is a some material is already coated over there, and there is a riding tire is there, discharge breaching, outlet to exhaust, some gas dust is exhaust, there is an outlet, it basically connected with some blower whenever it's required. There is also look and raw material feeding chute, driving assembly is there. So here if we go for the more closer, then there is in this assembly you can find many more small details of how the assembly work. This is just for the explanation purpose. And if you just go to the go check the side way, then this is the riding ring, feed inlet, motor reducer, coupling, support base, and this is how it actually look like in the industry. There are many things you can consider. Fitting holes are there, discharge devices are there, supports are there. When you go for the mechanical design of it, then this kind of phenomena, this kind of minded detail you need to take care of. Now on this tumbling granulation or any kind of granulation, the moisture content is also important thing. So if you how much moisture can be used in your operation, that you need to know before your operation or designing process take place. So we will just check that what is the effect of moisture content in the growth rate. So growth rate is very sensitive to liquid. Obviously, if you provide more liquid, then there will be slurry formation will be there. If you provide less liquid, then many more issues will be generated. Not much granulation is formed. So with increase in liquid content for fine powder leading to an approximate exponential increase in granule size. So there is one major serious issue. If you increase the liquid content, then exponentially you have to face the size of granule size can be increased exponentially. So that is also a major issue. So while operating this kind of size enlargement equipment. So that's why liquid content is important thing. And how can we go for it? So for lower viscosity liquid, I'm just waiting for the wait. So for lower viscosity liquid, granulation occurs when very close to the saturation of granule. So for if we use the lower viscosity liquid, then granulation can easily occur at the saturation of the granules. And we can use this estimated equation in order to find the moisture content. So omega is equal to epsilon rho L upon epsilon rho L plus 1 minus epsilon rho S. So epsilon is the porosity of the closed material, which we generally use denoted by epsilon. Rho S is the true particle density, solid particle density. Omega is the weight fraction of liquid, and rho L is the liquid density. Now we will try to solve one example. On the basis of, we will just check how this drum granulator can be used, and what is the different volumes and void volumes are there in our particles. And we can also check, or we will also check one the same example for the moisture content allowance whatever moisture content. So what weight of the particle is 2350 kg, okay, and the solid particle density rho S is 1360 kg per meter cube granulous solid need to be agglomerated in a rotating cylindrical drum which has the dimension like 2.75 meter long, 1.92 meter diameter. Okay, so we will use 2350 kg of this density material, and in this rotating drum which has dimension of this. So water density we always consider, assume 1000 kg per meter cube, we use as agglomerating aid, so it's binding material. And the only 2/3 of the drum capacity is recommended for optimal operation. If you want to go for the optimal operation, then only 2/3 drum can be filled, not more than that. So what is the void volume within the plate of the particles in this case? So we'll try with we start with rho is equal to 1360 kg meter cube, rho is equal to 1000 kg meter cube. Now void volume is equal to effective volume minus volume of solids. So total effective volume is there. We need to just subtract the volume of solid out of it. The effective volume is 2/3 of the total volume. So for that we need to find the total volume. So for the total volume, we have drum, cylindrical drum, so pi r square h. We just substitute the value, we will get the volume is, total volume is 7.962 meter cube. Now for effective volume, here we need to 2/3. So if we go for 2/3 of the volume, then there will be 5.12 meter cube is effective volume. Or you can just go for the 1/3 of volume. Total volume, then 1/3 total volume, V effective is equal to 2.654 meter cube. This is the V effective. Now if I want to find the volume of solid, then we have total volume, total mass of solid, which is 2350 kg, and we have solid density. So at the end we will get the total volume of solid is 1.73 meter cube. Out of it, this 2.654 minus 1.73 will give you the void volume. So void volume is 0.94 meter cube. And now we will use the same example in order we will find that what is the necessary moisture percentage to run the operation. What we can allow moisture allowance we will use to run the successful operation. So for moisture percentage, we have equation omega is equal to epsilon rho L upon epsilon rho L plus 1 minus epsilon rho S. So that's why. So epsilon is the void volume divided by effective volume. So we have all the values in our examples. 0.925 is void volume, effective volume is this, and at the end you will get 0.348 is the epsilon. Now you just have to substitute the value of rho L is 1000, rho S is equal to 1360, epsilon value you just got 0.348. So at the end you will get omega is equal to 0.2818. And if you get convert into the percentage form, then moisture percentage required to run the successful operation is 28.18%. So that's how you can use the simple methodology and simple examples, simple equations in order to find the moisture content, in order to find the void volume in this kind of this kind of size enlargement equipment or size enlargement operation. And you can from understanding these basic examples you can understand some of the assignment problems also. Now I just want to list out some more important topics which can be useful for your understanding, as well as basic problem needs to be solved. So mixture generator which can contain agitator. Okay, so mixture we require some mixing unit which can be for agitator or some other mixer. So mix particles in liquid to cause the granulation. So it contains the agitator which can mix particle in liquid. So it can process plastic or sticky material, because some hard materials there we can use. If we have viscous binder, then we can go for a mixture generator which can raise sensitivity to operating condition with regulators. The operating condition is anyway we can control on the mixing properties by mixer granulators. It produce small high density granules. So except few high intensity mixing systems, mixer generators are not feasible for very large throughput. So for large process, we are not generally use mixer generator. Granules from mixer may not be as spherical as those obtained by tumbling generator. Obviously, tumbling generator is very well known for that spherical granules. Control of amount of liquid and the intensity and duration of mixing determine agglomerate size and density. So we have to control this amount of liquid, intensity and duration in order to for the particular size and density. Now in the mixer generator, one class is low speed mixers, which is a pug mills and pedal mills. So they can be used for the both batch as well as continuous application. These mixers have horizontal troughs in which there is a central shaft switcher with arches with the brands, bar, rod, pedals. Essentially these are one type of twin rotor mixers. Okay, so as you can see, there is one shaft which is attached with different kind of blades, or you can say the pedals and all. This is a horizontal trough, and this may be single or double trough design. These are the type of twin rotor. So this is a twin rotor mixers. Now this is all about the low speed mixer. If you go for a high speed mixer, which is also known as a continuous shaft mixer. The continuous shaft mixer also have blades or pins for rotating at a very high speed. Okay, and there can be both horizontal and vertical shaft design are there. So very well known example is Sugi mixer and horizontal pin or peg mixers. So this is a typical picture of the Sugi mixer. As you can see, this is the vertical mixer. You just fed your material, and there is a shaft which has some blade and all. You are rotating by using the pulleys or some belts, and with very high speed that it can convert into the granules. Now this is a typical picture of this is a schematic as well, but this is a picture of Sugi mixture. In Sugi mixture, as you can see, this is the whole mechanical motor system, and this is the part where mixing is provided, very high speed mixing is provided, where you can get the final granulation process. Now batch horizontal and vertical high shear mixer. So for high speed mixture there is one other two different types, which is a batch horizontal as well as vertical high shear mixture. So if we talk about the horizontal side high shear mixer, then there is one, you can say one spherical structure in which you are providing some motor driven impellers, and there is a binding liquid can be sprayed over, and this chopper can be against rotating in order to control the particular size. And this is the actual picture of this horizontal high shear mixture. We talk about the vertical mixture just. Okay. So in the vertical high shear mixer, as you can see, the impeller and everything is on the vertical side rather than the horizontal side. So this motor and inkjet provide the vertical size, and liquid and chopper is there, air filter is there, liquidation is there. You just feed the material and it is mixed and then it will discharge. This is how it looks like actually. And this is the original photo of the vertical high shear mixture. Now fluidized bed granulators. So this is a typical fluidized bed unit where this is a air handling unit which has dehumidifier of air which we use for the fluidizing our material. With this control panel, and this is our part where processing unit, and here we put the solid material, we provide the air from below. So there should be some filter mechanism, so if some fine particles is there, it can be stored in some bag filters with the help of some blowers, and product discharge will be taken place at the end of the thing. So here you can say this fluid bag generator. This is a typical schematic diagram which is very well understood. So we fed our material in this, and then atomic nozzle air will go into the water and air. If we use the water as a binding material, then this is a typical example, and the air will be going out. This is air for the spraying purpose, and this granulation will form, and then it can be stored from this filter. So this is a typical fluidized bed granulators. If we go for the centrifugal granulator, then it's very simple again. Okay, so here we will feed our material. It has a feeding device also, and then it will go move in the centrifugal section. So this is the air chamber. Product will be outletted there, as air will be provided at the end, and solution sprays system will be there. And so this is all similar kind of setup like other generators. So this is also, you can understand that product outlet will be here, not a very complex thing. Now spray processes. You are using some spray processes sometimes. So in the spray process, why we are discussing about the spray processes, because for controlling the particle size, we are using the spray processes in which particle size is determined by the size of droplets of liquid or suspension. Whatever size of droplets and liquid suspension we are using, liquid or suspension we are using, that can be very important in order to determine the particle size, and it can be further controlled by the suitable spray nozzle. And for a given nozzle, the droplet size will be a function of both flow rate and liquid properties. Now viscous liquid tends to form large drops yielding large aggregates. So nature of the liquid can be important in order to find your final aggregates. So if you use a viscous liquid, then it can be yield large aggregates. And there is one important operation which is known as a preling. You have to take care of this, which will be very important topic. The preling, what is a preling? So when relatively large droplets are introduced into the top of the tall narrow tower and allowed to fall against the upward flow of air. So whenever we are introduce large droplets from the top of the tall narrow tower, and which can allow to fall against there is airflow is there, upward airflow, and it can allow to flow in bit from there. So this can be agglomeration process of spraying. It is known as a preling. This can be result in somewhat very larger drops yielding large aggregates. So we already discussed that if we go for the larger drops or viscous liquid, then the large aggregates needs to be there. So it's the same thing if we use the larger droplets in preling, then we will get the larger aggregates. So this is the like overall pictures of some schematic diagrams of batch fluidized bed, continuous fluidized bed. Different kind of fluidized bed can be also used for the size enlargement equipment. It's not like that or simpler kind of equipment is only used. Sometimes continuous disc is also used. As you can see, the oversized material product are all different. Continuous drum, continuous material coming, continuous exit. So these kind of processes are there. These are the actual pictures of the industrial schematic diagrams of the industrial level size equipment, size enlargement equipment. Now in this particular process, professor used many of the books, and I also follow the same. And the Paris Chemical Engineering Handbook is important for this, and then the same Unit of Chemical Engineering by McCabe and Smith, Unit of Particular Soil by Ortega Rivas, and some of the basic books which we are we are using. We have been using since first lecture. Now at the end, I just want to quote my idol, and as my habit to give some good quote at the end. So today I am discussing about just taking the quote from Swami Vivekananda, that never say no, never say I cannot. For you are infinite. All the power is within you. You can do anything. So always you don't need to belittle yourself. You don't need to never say no, and never you cannot do anything, because you are infinite. You all the power is within you only. Your brain and your willingness can be easily useful for doing achieving multiple things in your life. So just do hard work and be successful. At the end, I just want to thank you all for listening this lecture talk. And if you have any problem, you can contact me on my mail ID, which I have mentioned at the end of the presentation. And if you have anything, just let me know. Thank you so much. Have a good night and good evening.